Now it's time to present our keynote speaker. He is professor at Institut for Production Engineering and Forming Machines at Technische Universität Darmstadt in Germany. The title of his presentation is Towards Maximum Gain from Process Data in Sheet Metal Forming. I'm happy to give the floor to Professor Peter Groche.
Thank you very much for this very polite introduction, and thank you very much for the invitation you gave to me to share some of our outcomes of our research work together with many companies in the field of smart industry in practice. Well, starting point of my presentation is the question which we always ask to companies which we work with. Why do you want to use data acquisition in your processes? Well, typically we receive three different kinds of answers. The first one is, well, we have to, because our customer demands the data acquisition. The second kind of answer is, well, we have learned that data is the gold of the 21st century, so we are collecting data. We don't know why exactly, but maybe in future we can get some outcome from that. And the third answer we often hear is, well, we are curious. Maybe we can find some hidden secrets about our processes in our data. Well, in our work in Darmstadt, we try to systematically exploit data which is acquired in sheet metal forming processes and try to maximum the gain from this data acquisition. And I would like to share some of the results with you and some of the processes which we use to get the gain which we hope to receive in the end. This presentation has been prepared together with Christian Kubik and Andrzej Kokoszynski. They are both co-workers at our institute, and they are heavily involved in questions of digitalization and process data knowledge acquisition. The agenda for today looks like this. First of all, I will start with the challenges. We already heard in the introduction about the advanced sheet metal forming processes. I will then go to the acquisition and management of heterogeneous data, look then to the knowledge gain from process data, and look to the systematic improvement from data knowledge. And I will give some examples in use cases where we can see the potential of data in industrial applications. So as far as I see, okay, there is a heavy delay in the slide projection. So let's go first of all to our challenges which we have in sheet metal forming processes. Well, first of all, we can see that fluctuations are coming from the supplier side, where especially during these days, we can expect that prices, but also properties of semi-finished products vary a lot. Also, we can observe some fluctuations from the operator side itself, because the process conditions are fluctuating. And also, at the same time, we have to take into account that our customers of our products, they still require a high part quality, which of course is necessary for their business success, which of course is then the source also for the business success of all the suppliers of sheet metal forming parts. Well, now the main target for many of our processes is now, despite these numerous fluctuations, we want to achieve a target process state by, and this is our goal for this presentation, by gaining knowledge from data. Now, what is the starting point? And I mentioned in the beginning that starting points typically are not very clearly defined. We think that the starting point of any kind of data-related knowledge discovery is that you have a clear definition of your goal. And goals, as we have already heard in the beginning of this conference, are still the same. We still want to enhance our process reliability. We still want to increase sustainability. We want to ensure workpiece quality. We want to increase productivity. So there are many classical goals which we would like to fulfill and achieve. And now the difference, if you compare it to 1 decade before, is that we have additional opportunities, but also, of course, coming along with these opportunities by our data acquisition and data processing is also challenges. Now, what are the main challenges we have to cope with? Well, the first one is that the data we can generate and which we can achieve are heterogeneous. We will see what that means. Also, we would like to gain data knowledge from the data we received. And finally, the last challenge and the most important one is we want to improve something. We want to improve our systems or our processes. And there is a systematic approach necessary to come from the data which we acquire to the system improvement in the end. So how can we achieve that? First of all, let's have a look to our heterogeneous data. Well, data which we can see in our press shops are coming from process data systems, ERP, but also from outside our companies, for example, from suppliers or logistics, from personal data or product data. Additionally, we have data from our plant, coming from the machine itself, for example, the press forces or the power of our drives, which is necessary. We also can include additional sensors, either functional sensors, which are especially connected to machine elements, for example, shafts or screws. And we can use, of course, a variety of different conventional sensors. And in the diagram, you can see that it is expected that in the coming year, the amount of data which we generate in our production systems is increasing heavily. So the question, of course, is how can we, first of all, handle these heterogeneous data? And the second question is, how can we gain really some benefits from such kind of data? Let's first of all try to answer the question, how can we handle the heterogeneous data management in the context of our press shops? Now, first of all, heterogeneity is given, first of all, by the time series which we have, which can be covered by different kinds of either time series or also image data. And here we have to synchronize and also include timestamps to make use of the different sources in a homogeneous way. Then, of course, we have different data formats and different interfaces which have to be transferred to a unified data format for the specific application and for the specific environment. And also, we have to take into account that the data we would like to use are related to each other. For example, in multi-stage processes where we have a rolling operation, afterwards a stamping operation, or if you look, for example, to roll form applications, you have processing units which are shifted in the time domain. So we need some sort of data labeling and transformation so that we can have knowledge and can gain knowledge for our product part from our process data. So in the end, if you combine this, you have a database which is labeled homogeneous and has also timestamps. This is a prerequisite to start with the data management and also with gaining knowledge from your data. Now, what is the difference which we have now with the opportunities of our nowadays sensor technology compared to the past? And I think the first very important point is that we go from a product-related viewpoint to a process-related viewpoint. What does it mean? Well, if you go to the past and to the procedures which was applied there, we can see on the left side of this slide that typically we focus on our product and the product condition. For example, here, if you look to electric motors, you see to the different packages and you can observe by, for example, microsections, microscope images, visual inspections, the process induced product properties. But this procedure, of course, has a couple of disadvantages. First of all, it's very cost intensive. We have a high latency. That means we detect potential errors or necessities for improvement very late, so that there is a lot of scrap production maybe in between. And also this procedure is very time consuming. So these kind of investigations here have a very time-consuming and expensive drawback. And what comes also to our nowadays products is that besides geometry, more and more functional behaviors are of importance. For example, if you look to stem parts for electric motors, you see it's not only the geometry, but the geometry induces then some sort of magnetic properties, which of course then can be tested in the product quite late. That means the latency is even increased. So the alternative to this point of view that you investigate your product property is that you use an inline inspection. Inline means during the process without any delay of your process itself, because then you have a fast, hopefully accurate and economical quantification of your actual process state, which allows you to predict the product state. So this is one important difference between the old and the new kind of process observation. Now you might argue, well, we already have some sort of process observation since maybe 3 decades established in industry. And we know that there is a lot of process observation and process control where we make use of characteristic curves, where we define some characteristic values. For example, threshold values, envelopes, or windows. And such kind of data acquisition and data knowledge generation is used to detect fault detection. So the only information you can get from such kind of observation is whether the product is okay or you have a faulty quality. With the new possibilities of sensors and data models, we now can enhance the knowledge activation and knowledge discovery by a combination of our sensors and a model. And this enables us to give us the opportunity to have more knowledge about our products, but also about our processes. What does it mean? Well, first of all, we can see that we can observe differences and changes of the state of our production system. For example, wear of tools, as shown here. But also, we can detect the causes for some kinds of deficiencies. That means we can immediately from our data, which is then used in our models, detect what kind of machine or tool or semi-finished product component is responsible for the product properties and maybe also for our deficient product properties. Now, if you want to achieve this goal, we have to use a combination of sensors and models. And that allows us to use our process data for data knowledge. Well, in the conventional way, we have some procedures established which are called knowledge discovery in databases, which make use of such kind of approach. They start with a data selection, a data preparation, then some sort of data mining and interpretation, and that creates some data knowledge. Well, this conventional way of knowledge discovery in databases, of course, is not sufficient if we compare that to the goals I mentioned in the beginning. Because with that, we don't have a transferability to other processes, and we also have a lack in feedback for knowledge, which is necessary to improve our systems. So therefore, we decided to extend such kind of knowledge discovery in databases approaches and extend it to in a way that we use our data knowledge to create some dependencies and interlinkages between different components in our system. This is based on a data acquisition procedure where we select sensors in a way and on locations and with properties which are sufficient and which are adequate for our forming processes. The data then are pre-processed. For example, they are transferred to the frequency domain. They are transformed to some features. This allows us to model the correlations which we would like to see. We can validate that and have then the data knowledge which we can use in the next step for gaining system knowledge. And system knowledge means that we explain the results which we receive from our models which are here discovered in our correlations, and from that derive those actions which are necessary to improve our systems. And by that, we can have a system improvement based on data we acquire during our processes. So this is now here on a very theoretical and maybe abstract way, and I would like to go a little bit further and look to some use cases where you can hopefully see the benefit in real applications. Let me start with one where we see that the process reliability should be enhanced for stamping processes. Stamping means, in this case, we have a combination of blanking processes and afterwards bending processes. And as I mentioned in the beginning, one of the challenges for many companies in this way is that our semi-finished products have fluctuating properties in terms of thickness or in terms of strength. That means if you go through such kind of line, you will detect that your final product, here described by a bent part with a bending angle, will also be fluctuating. So in this case, the challenge is that you first of all have to have an adjustment for your bending process, but you have to know the necessary adjustment properties in order to have an increase of your process reliability. So how can we manage that? Now, in this case, we have a combination of knowledge discovery from our stamping process, which is then feed forward to our bending process in order to adjust the tool movement during our bending process. This is achieved in the following way. We take our forces from our cutting processes, and these force slopes are then transferred and modeled into features. For example, shown here in the principal component analysis, we see one of these eigenvectors. These eigenvectors are then transferred via a model, in this case a neuronal network, to the deviations of our properties, which are important. In this case, the change of our thickness from the nominal value and the deviation of our strength from the nominal value. Now, if we know such kind of deviations in our semi-finished products for each part, that means 100%, we then can go in the next step to a second model which allows us for adaptive control. Because then, now we are able to adapt our process parameters, in this case the depth or the distance and the travel of our part for a punch for our bending operation, accordingly to the deviations which we have in the material properties. And as you can see in this chart, that works quite well, even if you have big differences in your properties of your semi-finished products, as shown here. Only a very few parts then are out of tolerance due to, of course, some still existing model errors. But in general, you can see that you have a very clear and very good reliability of your process, improved drastically by using such kind of smart data evaluation and adaptive process control. Well, in our next example, we would like to show how we can increase sustainability. And this example is not only selected for increasing sustainability, it is also selected because in this case we don't need data-driven model. We can use a conventional engineering model which is based on features which we derive from our physical knowledge. This example is coming from a roll forming technology, where you see that in modern roll forming lines, we have the possibility to also acquire a lot of data. This can be torques, for example, but it also could be the current which we use, or forces, or positions of our tools, and also, of course, product sensors, for example, profile sensors. Now, one of the challenges in roll forming is that the conditions of your slip in each stand is unknown in the beginning. That means that we have rolls which have different diameters, so the circumferential velocity in each surface point is different. So ideally, we would expect that during the transport of our sheet through our roll forming line, we would have a feed forward and a forward movement in every roll. But in reality, we can see that our diameters are not so well adjusted. So we have slip conditions which lead to a non-negligible energy demand, which is, of course, a waste of energy. And in several investigations, it was found that about 20 to 40% of the energy could be saved by adjusting slip conditions. This can be done, of course, in advance by finite element simulations. But even here, we have some uncertainties in the modeling and also, of course, in the boundary conditions, which we can use, for example, the stiffness or the state of our tools in the actual time state. Now, the results of such kind of data analysis is shown here. The starting point here for a well-adjusted roll-forming line is seen here on the left side, where you can see that the necessary moment at the different drives is very different. In some cases, even negative. That means in one cases we are accelerating, in others then we are decelerating. So that cannot be the optimum state of our energy consumption. So therefore, we can see that here in stand number 2, we have very high moments. And by adjusting our geometry, in this case, the geometry of our rolls, we can see that in order to lower the necessary amount of energy or the necessary moment, we can have a change in our tool geometry, and that helps us to optimize in a first step our roll forming line. But we still have some negative values of our moment, which in the next step could also be optimized by additional tool geometry based on this data. And in the end, you see that we have a moment in each cent positive, and also we see that we have a more homogeneous distribution of our necessary moment in every stand, which will lead to a more equalized wear in every row. So in this case, there is a clear engineering connection between data and system improvements. In the next step I would like to discuss is how can we ensure our workpiece quality? Because workpiece quality, as I mentioned before, is necessary for geometry, but also necessary, for example, for magnetic properties. And you can see here that if we use, for example, a very sharp edge in our cutting tools, we have a very low residual stress level in our parts afterwards, which goes along and comes along with a small specific loss in the later application of our magnetic parts. On the other hand, if we have a worn tool, we have a changed geometry, which comes along with a higher residual state of stresses, and that comes along with increased loss in our magnetic properties and our electric motor. So the goal here is to ensure that we can detect the wear status of our tools continuously and decide whether we have to have a remanufacturing of our tools or an exchange of our tools at the right point. So how can that be handled? Well, you see here some examples of worn tools from no wear to critical wear. And the question is, can we detect such kind of wear during our process? And you see here some examples of force time plots for different kinds of wear conditions, where you can see that you detect differences in the force curve, which could be explained by some engineering models, but with a very, very high effort. So it is more advantageous to use directly data-driven models, which help us then to detect such kind of wear states from our data. And this data can, of course, be force data. But force data in our measurement in a production line are quite expensive. So therefore, it is also necessary to think about alternatives. One alternative could be to use acceleration signals, because such kind of drastic force decrease come along with high accelerations. So we use such kind of acceleration signals, use them for a machine or deep learning model, and try to identify the wear states of our tools. The result is as follows. You see here different kind of wear states which have been investigated in different kinds of time series. This is a typical kind of acceleration plot over the punch penetration. We use a deep learning model to derive some features, and these features help us to detect whether we have wear or critical wear or no wear. And the prediction quality from this model, we have to say, is good, but of course, if you compare that with conventional production requirements, it might not be totally sufficient. So there is, of course, some room for improvement, but you see that the prediction is more or less in the range of 98%. So that could be, of course, a first step to detect wear. But with this detection of wear, we might be able to reduce some scrap. But the more important point for many manufacturing operations is how can we increase our system itself? So what we now need is we need an explainability of our model results. And that is an area which can then help us to increase also the design of our tool systems and machines. Now, how can we now achieve an explainability of our model results when we use black models? That means models only driven by data. Well, we can look to image correlations and image processing, where we have a similar problem, because there are also classification schemes which try to classify objects on images. And the question here again is, where is the critical area which decides in the end which kind of class is used? This can be identified with algorithms like, for example, class activation mapping, and that helps us to see the hotspots or the heat, which is in the end responsible for ordering and for selecting one specific class for one object. So our approach was to use the same idea for our time series. And what is the result in this case? Now we can see our normalized chem value, which gives us the relevance of specific features for our classification. And shown here is the acceleration over the time. And you see that especially in the beginning, we see that there is a high relevance of our data for the classification of the wear status. Well, from an engineering point of view, that means in the beginning of our phase here, we have the relevance. And that is the investigation, or that is the result of our modeling, that we see that this critical time phase is responsible for the wear state or not. For engineering work now, we can go to our system and ask which kind of our tool system should be changed. And now you know that in cutting operations, we have different kinds of wear. The wear can be in the cylindrical area, but it can also be at the edge. In this case, from an reverse engineering point of view, it is very clear that we have to increase the resistance of the cutting edge in order to have a higher and longer tool life in cutting operations of this kind of process. So from this example, you can see that although we use black models, which are purely data-driven, we still can connect it with some engineering knowledge and can have now the basis for engineering improvements, system and tool improvements in our processes. Now, let me summarize and give some conclusions. Well, first of all, data-driven models, as we have seen, enable a quantification of process states by gaining knowledge from process data, and that can help us to react very rapidly to changes in our manufacturing systems. That can help us to reduce machine downtime. It can help us to achieve higher workpiece quality. It also can help us to minimize energy consumption. And there are some indirect benefits for industrial applications, which I would like to highlight. We can see that the investing cost can be quite significantly reduced, especially if we use low-cost and easy to integrate sensor technologies, acceleration, for example, instead of force. And we can increase the information value by gaining knowledge from deficient data via data-driven models. So with that, I would like to end. I would like to thank you for your attention and for listening, for the invitation once more. And of course, I think we will have some opportunities for answering questions and also for having discussions in our breakout or Q&A session. Thank you very much.
So thank you very much, Professor Groche. It was fantastic to hear you and see you coming back also again in the conference. So I'm very happy to hear you. And we have some questions, actually. I will take one or two here, and then we will meet also in the Q&A session later on for more detailed questions.
Yes, sure.
But I have one about the sensoring. For the bending example, the first one you had,
Yes.
how would the result react from the latency and calibration problems of sensors? How much of a problem would that be in the overall picture?
Yes, a good question. Well, of course, if you select a sensor technology for your specific manufacturing task, you have to take into account latency, also, of course, your time-wise requirements. So in this case, we use piezoelectric sensors in order to achieve the necessary data. And a sensor and a measurement line which enables us to be fast enough for the next step and in order to achieve the required actuation. The model which is used then for the actuation is a linear model. So otherwise I think we would be in trouble for fast punching processes to have fast enough actuation available.
So thank you very much. And I also have a question from Eric, who will be the next speaker, so we can't be in the Q&A.
Okay.
So it's a more detailed question. On the whole project time, how much would you estimate the data preparation process going from time series to homologous labeled data took? So in the whole project, was that a big part?
Yes, sure. That was a big time. It's still going on because there are so many possibilities to derive from data specific features. And in the beginning, we started with a very clear engineering approach. That means we wanted to understand what kind of features are necessary with our physical-based knowledge. And it was interesting to see that when we came to the features-based more on data-driven models, we achieved very rapidly very promising results. That was on the one hand impressing. On the other hand, of course, it raised the question, what is the value of engineering knowledge in this context? So therefore, yes, that's an important point. And of course, it takes time and you have to do that carefully.
So thank you very much again, and we'll meet again all who want to talk more to you in the Q&A session later on. So now back to Ingela.
Thank you.